Welcome. Today I'm going to talk to you about the last of Newton's laws that we're going to cover in class. It's really kind of the fourth of his laws of motion, if you want. It's a very special case, and it specifically deals with the cause of motion that is gravitation. Here we've had the first law, which is that objects move in a straight line at the same speed unless acted upon by an external force. And then if you do have an external force, an external net force, we can use Newton's second law to be able to describe the acceleration that it causes. And then in the third law, we talked about the fact that applying one force to one object implies that there will also be a force back on the first object of the same size and in the opposite direction. And so together, those make a really nice description, general description of how motion works. But there's a special case, and that's the special case for gravitation. And really, it's important because if you remember, Newton was trying to answer the question, why does the moon go around the Earth? Really seems like an obvious answer, right? And you think, well, he was really supposed to be smart. No, it's not really that. If you look back, you think about it, people didn't really know. And we take it for granted now that the laws of physics that we understand that work on Earth also work everywhere else. But Newton was really the first one to come along and say that, I see this apple falling here next to me. I wonder if that's the same force that's keeping the moon going around the Earth. That's a huge leap for two reasons. One, the moon doesn't hit the Earth, and two, that the fact that the moon is very far away and it's in space, and space is different somehow from Earth, and no one has ever been to space at that time in 1666, 1667. That's a huge deal, right? That he was coming along and saying that making these claims. Turns out that he was right because he's a genius. But that's a huge step for him and his theories, and also for physics. And so this is kind of a big deal right at this point. So he came up with this thing, and we're calling it universal because it happens this way, approximately, for all objects everywhere. And then gravitation, because there's this effect for gravity, right? And so we've talked a little bit about that. So you're starting to get a sense for what gravitation is. Gravitation is also often depicted as a field, and so I wanted to include a field diagram here. So here's the Earth, and the center of the Earth is right about there, as you might imagine. And you can see that the field lines have all been drawn with arrows pointing towards that center of the Earth, the center of the Earth's mass. And so if I take an object, let's say a rock, so here I have a rock, and I hold it so that it's motionless with respect to the Earth, right? So that I'm far up in space. I have this rock. I'm holding this rock, and the Earth is stationary below us. If I let this rock go, these lines of force tell us that it will start to accelerate towards the center of the Earth. And so at some point, it's going to collide with the surface. And so that works for objects that are stationary. What about an object like a spaceship? And so let's say I have a spaceship. I'm going to draw kind of a bullet-shaped spaceship here. And normally it would travel in a straight line, but you notice it's in this field. And this field has these lines of force that go in towards the center. And so as a result, we might find that the path is actually kind of curved because of this gravitational force. And the other part about this, or the cool thing about this force diagram, force field diagram, is that as you get closer, you can see you're closer to the center of the Earth, closer to the surface of the Earth. That means you can see that the arrows get closer and closer and closer. They get more densely packed in there, and as a result, we say that it's stronger when you get closer to it. So this rock, if it's very far up in space, may have a smaller force that's applied to it, but then as it gets closer and closer, that force increases in size until finally it hits the surface of the Earth. Now it's weird to think of the field of the Earth to be in a sphere like that, because we don't normally think of the Earth as a sphere, because we're only used to it being flat in our local region. That's pretty flat, and so we're used to the field lines coming straight down parallel into the Earth. And so if I take that same rock and I place it there, it's going to fall straight down towards the surface. No big deal, right? And that's because, again, the Earth is pretty big. And so locally, in the small region, if we're kind of only looking at around what's around us, we can pretend it's flat because it's pretty darn close to flat. Anyway, so mass has two different aspects, right? The one aspect is it produces this property that we know of as inertia. And so we explored that quite a bit. Obviously, things move in a straight line at the same speed, Newton's first law and all that. So mass produces this idea of inertia. It's a resistance to a change in motion. Then, for reasons we're not quite 100% sure about, it also produces gravitational effects, this gravitational field. So gravitational fields are also produced, and both of them are based on how much mass the object has. So the more mass, the more inertia, and the larger or stronger the gravitational field. Now, if you have a large mass and another large mass, the gravitational fields of both interact and attract in such a way that you end up with a much bigger force. And so you can start to see that the universal law of universal gravitation must be based on the masses of the objects, right? And as we said here, you can see the field lines get more and more dense as they get closer, which means that the force gets stronger as you get closer to the surface of the Earth. And so there must be also something about distance, right? So distance must also play an important role. So the distance between the object's center of mass and the Earth's center of mass, for example, actually between the centers of masses of any two objects. So the distance between them is important as well. And so we've got these two things that are going to determine what the strength of the force is for gravitation. And so here it is, without any further ado. The universal gravitational law states that the gravitational force between any two objects is equal to this is a number right here, capital G, called the universal gravitation constant, times the first mass times the second mass divided by the distance between them squared. Now, a couple things real quick. You can see I rewrote it. Here it is, the sort of the nice and neat way. And they just pulled the big G out, so it's not a big deal. Is big G the same as little g? Absolutely not. Okay, little g is 9.81 meters per second, and it's an acceleration that is experienced by objects that, like this guy right here, are close to the surface of the Earth. This capital G right here is nothing more than a unit conversion factor. And it's a very, 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 very small number. So here it is. Big G is equal to 6.67 times 10 to the negative 11th newtons times meters squared per kilogram squared. The whole point of this universal gravitation constant right here, this big G, is to convert the units on this side into newtons. That's all it's there for. So it needs to take these ideas and convert those units, so kilograms times kilograms divided by meters squared, into newtons. And so that's where that comes from right there. And so it's a really small number, 6.67 times 10 to the negative 11th. I'm going to go ahead and write that out. Look, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, like that. Whew. Newtons, meters squared per kilogram squared. Holy cow, look at how small that is. That is a super small number, so you can be thankful that we're going to use scientific notation to talk about it. So, why don't you feel a gravitational attraction between you and your pencil? Well, the answer is buried in this gravitational constant right here. Check this out. Let's say that you have a mass, let's just keep the numbers simple here. You have a mass of, I'm going to go ahead and write it down here, 100 kilograms. And let's imagine you have a pencil, just again to keep the math simple. Let's say that 0.01 kilograms is your mass of your pencil, okay? And let's say you're 1 meter away from each other, okay? So that times big G right here, right, is going to tell us how much gravitational force there is between us. So 100 times 1/100th is just 1, divided by 1 squared, which is 1. So 1 over 1 times 6.67 times 10 to the negative 11th newtons per meter, newtons meter squared per kilogram squared. Whew. So how much force is there between you and your pencil? This much newtons. So you can see why you don't ever experience that. You would need highly sensitive, highly precise tools to be able to measure that out. And so you don't often talk about it. But it's important to remember that everything, literally everything that has mass produces a gravitational field. One other thing that's important, do you notice that here it says F1, and here it says F2, and here it tells you that F1 and F2 are equal to each other. Don't forget, Newton's third law totally applies. If the Earth is pulling me down with a force of 800 newtons, I'm pulling up on the Earth with a force of 800 newtons. Why? Because of Newton's third law of motion. I'm resisting a change in my motion. I have inertia, I have mass, therefore I must also apply a gravitational force to the Earth. Why doesn't the Earth move? Well, because the Earth has a mass of about 6 times 10 to the 24th kilograms. So me applying 800 newtons of force to it would give it an acceleration that we just would never be able to measure. Plus, there's all likelihood that there's another deglopper on the other side of the Earth that's balancing out my force, and so therefore the Earth is in equilibrium. There's probably not. There is actually another Jeff deglopper somewhere, but not on the other side of the Earth. Anyway, so there you go. Did we hit them all? Yeah. All masses produce gravitational fields, causing them to pull on all other masses. Yes. The strength of the field is determined both by the size of the mass and the distance between it is from the test object. Okay. So don't forget, that is a distance right there between the two. Important to note, it's often written as an R because oftentimes in astronomical discussions, we're talking about spheres, right? And so we're talking about a field that is spherical in shape, and so therefore it should be a radius rather than a d for distance. So that's why that is. Sometimes you'll see a little d down there, but I don't do that usually. And then last, gravitational is a universal. Gravitation is a universal phenomenon and not a special feature of the Earth. Again, a huge step. Who knew that he would be right? There was no way to test it until many, many years later, although it made sense. And so, of course, when people read it and they saw it, they said, "Oh, that totally makes sense." And then from this law, he was able to get some mathematical confirmations as well. And that mathematical confirmation really was what did it for him. Anyway, so there it is. Hope you enjoyed it. This is basically our one well, no, we have one other formula. So this is our main formula for this unit. So, and it's a quick unit, so hold on tight. We're going to go fast. Let me know if you have any questions. Good luck.